Great to see everybody here today. Good afternoon or morning, depending on where you are. So I thought I'd first kick off by reminding everybody what the mission of the PISMIT panel is. We're the Process Studies and Model Improvement Panel, and our mission is to reduce uncertainties in general circulation models used for climate variability prediction and climate change projections through an improved understanding and representation of the physical processes that are governing climate and its variations. And we go about that doing a lot of different from a lot of different avenues. One of the ways we gather information is by having these hopefully regular monthly-ish webinars where we hear from various process studies and their experiences in the field and lessons learned. Today, we will be hearing, this is the first in a series of 2 webinars that is going to focus on the Multidisciplinary Drifting Observatory for the study of Arctic climate, which I definitely had to look up before this because we normally refer to it as MOSAiC, and that's much easier to remember. Although, Matt, I'm sure you have that, it flies off the tip of your tongue, but MOSAiC was the culmination of roughly about 10 years of work and planning that Matt, I'm sure, was heavily involved in. And it provided an extremely unique data set that we will hear about today. The total cost of MOSAiC I looked up before the webinar is roughly about 150 million US dollars and had significant investments from both NSF and DOE. So today we're going to hear from Matt Shupe and Amy Solomon, both of which played significant roles in the MOSAiC campaign and the science work that's moving forward. First, we'll hear from Matt. Matt is going to provide us some of the early insights from the MOSAiC campaign, as well as an overview of the observations, what was done, and what the potential path forward using those is. Matt Shupe is a senior research scientist at the Cooperative Institute for Research in Environmental Science at University of Colorado Boulder. And has been there since 2004. Matt received his bachelor's in chemistry and mathematics from the University of Puget Sound and his master's and PhD from UC Boulder in atmospheric and oceanic sciences in 2006 and 2007. Matt has worked relentlessly for more than a decade to make MOSAiC a reality. And since 2011, he served as the co-coordinator of MOSAiC. In addition to his leadership role in MOSAiC, he has served a wide range of other scientific leadership roles in other field campaigns from NOAA and DOE, including ARM MPACE, NOAA Search Arctic Atmospheric Observations, ARM ISDAC, ASCOS, StormVex, and the list goes on, but I'll stop there. But Matt's research is primarily focused on Arctic clouds and atmospheric processes and their interactions with the surface using primarily ground and airborne observations. So secondly, we're here from Amy Solomon. Amy is a research scientist at NOAA's Earth System Research Laboratory in Boulder, Colorado, where she's been since 2002. Amy received her bachelor's in physics from UC Berkeley in applied mathematics master's degree at CU Boulder and her PhD in atmospheric dynamics from MIT in 1998. Amy's research interests include cloud microphysics, radiation and dynamical properties and processes, cloud interactions with the boundary layer and surface, as well as short-term Arctic forecasting and Arctic meteorology and climate. In her work with MOSAiC, Amy serves as an international lead to organize the forecast guidance in support of the MOSAiC campaign. And today, Amy is going to share with us some of her current and future modeling efforts involved with the MOSAiC data. So with that, Matt, take it away.
Thanks for having me. I'm going to talk about MOSAiC. Thanks for presenting that acronym. It's a fantastic acronym, I think, and it really does get at the heart of what we're looking at here. MOSAiC, you can think of mosaic of ice flows, mosaic of processes, and I'll take you on a little journey here. The title here is Challenges and Opportunities of a Year in the Arctic Sea Ice, and I think that those two challenges and opportunities really go hand in hand, and that's kind of the theme of what I'll talk about here in this introduction. And you know, based on the guidance, I'm going to try to focus on some of the kind of programmatic things and international connections and some of those kind of aspects. So just very briefly, though, to set the context, I'm not going to dwell at all on this, but motivations, why we go to the Arctic. Well, of course, the Arctic's changing rapidly. Sea ice is in decline. There's amplification of temperature changes in the Arctic relative to the rest of the globe. Our models are challenged there to represent things like the declining sea ice. There's all kinds of emerging operational and management needs in the Arctic. There are questions about the linkages between Arctic change and the rest of the globe. And of course, we have very few observations there to really build our knowledge and our models upon. So based on that background, we really started putting together plans for an expedition into the Central Arctic. And as Patrick said, this has been a long-term process. I've personally been working on it for 12 years, and it was very much on the international stage. And I'll touch throughout this little presentation on the international linkages, because I think that's a really important part here, and it was one that I was asked to speak to. So importantly, the International Arctic Science Committee was where a lot of these initial kind of plans started to be discussed, and that was really important to build the connections across different nations and different agencies. And so that's kind of a foundation for this. The expedition was designed to be interdisciplinary. So looking at the Arctic atmosphere, sea ice, ocean, how they're interacting through physics, chemistry, biology. So it's really a cross-cutting project in the Central Arctic. Importantly as well, we wanted to look at the annual cycle. So often in the Arctic, you go out there for a few weeks or a few months, but covering the whole year is actually really important to look at things like interseasonal linkages and connections and processes that play out year round. These are really important, and a lot of gaps in our observational kind of past. Also, we want to have this multi-scale approach, and my next slide will focus on that a little bit. But importantly, this whole concept was really founded through this discussion between the modeling and observing communities jointly. And that laid the foundation for this concept in terms of how we designed the field operations and so much more. And so a little bit of a look at that, this multi-scale approach is, we have this ship that we took out and plugged into the Arctic sea ice. So I'll show you some pictures of that ship coming up. And it really was the platform for this central observatory. We had the ship, we had some things on the ice near the ship, and this was, extremely comprehensive measurements, looking at coupled system processes across this atmosphere ice ocean system, and really diving into the processes on kind of very small scales. And we also set up this distributed network of other assets out on the ice, spread out across a 50-kilometer approximately domain around the ship. These are autonomous buoys, these are unmanned aircraft, other systems for providing some of the spatial context across what's approximately a model grid cell size. And of course, we want to link with Pan-Arctic observations from, we had an aircraft campaign, we had some collaborating research vessels. Of course, there's land-based stations, there's satellites, buoy networks. So really linking our localized observations with Pan-Arctic concept. And so, of course, these all then plug straight into modeling at different scales. So this is kind of the design here, to try to plug in and have an impact on models that could look at processes, models that could study regional processes, and on up to global models that have to represent the Arctic, of course, and its changes. So kind of schematically, these are some of the areas, somewhat atmospheric bias because I'm an atmospheric scientist, but some of the different areas that we study and some of the processes we studied here with MOSAiC. And so you can see some of the key themes, of course, atmosphere and all kinds of things going on in the atmosphere, sea ice and snow, looking at things like deformation, drift of the ice, ponding, ridging, the ocean circulation, turbulence, stratification, the ecosystem that's playing out, that's living in the ocean and the sea ice and interacting across scales. And then, of course, biogeochemical processes that link a lot of these, chemical and biological processes across the system, linking the ocean, ice, and atmosphere. Overall, our leading science question is, what are the causes and consequences of an evolving and diminished Arctic sea ice cover? So Arctic sea ice and its changes were really the centerpiece here. And we're looking at all the different interactions in the system related to the changing sea ice. What happened then? Well, we took the Polar Stern, this beautiful icebreaker from Germany, and took it out into the Arctic for a full year. And this is from September 2019 through October 2020. So we're not even a year out of the field yet. This little schematic on the left shows where we were, and the dotted lines are where the ship was moving, and the solid line is where it was drifting. And so we basically, in the end of 2019, took the ship out and plugged it in the sea ice and passively drifted with that ice for the better parts of a year. And so this passive drift follows what's called the transpolar drift that goes from the kind of Siberian sector near the North Pole, which you see the cross here, and out towards the Fram Strait in between Greenland and Svalbard. Turns out that we drifted faster than planned, and actually we got all the way to the ice edge by the end of July. So we actually had to take the ship back up further north, plug it in near the North Pole to finish out the year. So that was an unplanned activity. And we had a few other, snafus along the way, and I'll get into talk about those a little bit. But you can generally see where we were and the trajectory and some of the dates involved in this drift across the Arctic. Well, we took so many observations. I showed that schematic before, and I'm not going to try to even list all the observations here. If people have questions, I'm happy to dive into it. But we had observations of all types. This was really fantastic. As Patrick said, I've been in a lot of field programs. Nothing ever like this in terms of comprehensiveness. We're sampling, ice cores, snow, water samples, all kinds of biological critters, air samples. We had remote sensors looking at the atmosphere. We had remote sensors linking in with kind of satellite-based sensors. We're measuring fluxes of gases, of energy, of momentum. We're looking at the reflection off of melt ponds. We're using tethered balloons and unmanned aircraft. So many different approaches and perspectives and observations. So a really fantastic, comprehensive observational data set out there. I want to focus here largely on some of the challenges and successes and lessons learned along the way. And these were some of the things that Patrick asked me to speak to. The first challenge is COVID. Well, I'm not sure what we can learn from this, really. This was unplanned. Of course, we had no plan for dealing with the global pandemic, but it was actually nearly fatal for the mission. Fortunately, though, through perseverance, ingenuity, and a lot of international collaboration, we were able to work out a way to keep things going in the field in spite of the kind of global. But if we're thinking more on the natural scales, well, our challenges started at the very beginning. Just finding an ice flow, right? We need to have an ice flow that we could set up a bunch of stuff on. It had to be kind of stable. Turns out the ice was really thin. Of course, we knew this, right? This is why we're going there in the first place, because the ice is thinning. So eventually we did find an ice flow. And our success here was that we found this flow that actually did last all the way until it came to the ice edge. So in spite of the thin ice, we actually found some success there. Another huge challenge was darkness. But again, this was part of the deal. We knew we were going there for the whole year. We knew it was going to be bitter cold. And it gave us the opportunity to have these kind of rare wintertime observations. This is one of the really remarkable things about MOSAiC, is this dark season when so few observations have been made in the Central Arctic. So this is a huge opportunity for our. A fourth big challenge was ice dynamics. The ice really liked to break a lot. And perhaps this is part of the deal with ice getting thinner, and perhaps it was some other forcing involved, but wow, the ice was breaking a lot. And this, of course, led to damage of instrumentation. This interrupted a lot of our measurements at times. You can see some of these pictures here with power lines that we had going out to different stations that were getting separated by a lead. You can see stations that are getting tipped upside down. Very dynamic scene there that was extremely challenging for our operations. But on the other hand, we were embedded right in the middle of this very dynamic Arctic. This is the current day Arctic, and we were there in the middle of it, experiencing it as it unfolded. So one key lesson here, though, that I'm taking out of it, and I pose it in terms of a question here, is were we properly prepared for this, all this dynamics? And I would say at many levels, we were not, right? We have all this experience from decades past and from the Arctic past that, is somewhat applicable today, but I think is becoming less applicable, right? Operating on a very thin ice cover is not like it was in the past when we had thick ice. And so these are, it's bringing up ways in which we're going to have to adapt our observational strategies to really continue to monitor the Arctic as it's changing going forward. One last big challenge was that this year was actually kind of anomalous in terms of large-scale circulation. And the challenge part of it is that the winds kind of set up in a way that it blew us across the Arctic much faster than planned. So that was a big challenge. But it also provided this opportunity for us to kind of contextualize our observations at MOSAiC with this kind of larger scale scene that's playing out with very high values of the Arctic Oscillation Index, anomalous winds, a lot of drying and warm temperatures in northern Siberia with fires. So it was a pretty crazy year in addition to the COVID scene. But we get to have, you know, these great observations right embedded in the middle of this kind of large scale, interesting kind of telecommunication pattern with the rest of the globe. Speaking a little bit to the international part, we had 20 nations involved in funding this thing, and 37 nations involved in terms of the people that were on board the ship. 7 different icebreakers or ships, more than 80 institutions, more than 400 people went to the field. So this is really tremendous. Here's the $150 million figure that Patrick mentioned, and about 40 million from the US. Those numbers are actually outdated already. There's been more investment since that time, and there will continue to be more investment. But you can see this highly international flip. And I wanted to just make a few comments about that. You know, I was asked to comment on the international process. And so I've kind of put this in the form of steps for success, right? How do you have a successful international activity like this? And one of the really important things is openness and flexibility, right? We all bring our different perspectives, and you have to be open to other people's perspectives. You have to have connection, build trust. And so for myself, over more than a decade, it was a lot of handshaking. I guess maybe we don't do that as much anymore, but a lot of FaceTime, right? You have to interact with people and build trust. You have to develop a shared vision, right? Something that people can resonate with across different nationalities. You have to gain high-level buy-in from important international institutions, agencies, and of course, funding bodies. That's really important. You have to share ownership. It's always easy for us to try to own our science, but in the end, you need to share that with others, right? In order for them to want to invest and engage as well. And so shared ownership is really important. You have to work collaboratively together. This was awesome in the field. We had things like, hey, Mondays we'd go out and do ice core sampling, and there was this international team of people that would go out and do those kind of things together, working together. Data policy. You have to share data. That's so important, right? If you really want to have an international activity, you have to share. And so that's something that we've continued to grapple with, but I think we've done a pretty good job with sharing our data. And you have to have inclusiveness, right? With publications, with research, you have to include people and build teams. So MOSAiC was really successful, I'd say, based in large part because of the broad international foundation and the broad international contributions to it. Just a couple summary slides here. Distinct scientific outcomes and successes. Well, we had this extremely comprehensive set of measurements now. This is a huge success, I would say. It wasn't necessarily everything we envisioned, but it is still a remarkable data set. We captured really key seasonal transitions over a full year, and a lot of important events like big storms, fresh water lenses on top of the ocean, ice flow breakup at the very end, aerosol formation events, ice dynamics, so many different aspects that we captured over the year. We were able to look at midwinter biology. We have precious few observations of biological activity in the Central Arctic winter. We could map the top and the bottom surfaces of the ice together over the course of their evolution for a year. We have this sophisticated remote sensing program that's really going to provide this ground foundation for a lot of our satellite observations in the Arctic. This is the most comprehensive Central Arctic set of observations of clouds, aerosols, atmospheric profiling really ever attained. We had 4 times daily soundings, which will be a really awesome data set for evaluating the impact of soundings on operational modeling. We had our distributed network that allows us to look at sub-grid scale processes for how do we take these processes then and implement them in models. And of course, we're spinning up all kinds of modeling projects right now that are harnessing different aspects here, and you'll hear about some of those from Amy. Over the course of this year in the Arctic, it was a huge challenge, and most of those challenges were also tremendous opportunities for us. The thin dynamic ice was the biggest of those challenges, but it was the opportunity for us to be right in the middle of the Arctic and Arctic change. We did tons of science, packing it as much as possible. We had very broad participation, internationally, interagency, interdisciplinary. We had media, we had outreach, all kinds of people out on site. We built a lot of capacity. We've really trained this new generation of scientists that can be the future of Arctic research. And we've brought in new concepts for how to conduct research on a thinning Arctic ice pack. And importantly, we've created this legacy of data for all to use. And that data is going into a number of different archives that can be available for the general community. And there's so much more to come in the coming years as we really pivot towards the analysis of the data. We dig into the data and figure out what it's telling us and how do we use that to better understand the changing Arctic and to better model the changing Arctic. So with that, I just put up a few icons here from our, a few logos from our funding bodies in the US, and I'll point you to a couple that have a lot more information, and I'll say thanks for your attention.
Thank you, Matt. We'll save questions to the end. Amy, do you want to go ahead and take it away?
So yeah, thank you for this opportunity to present to your panel. I'm really looking forward to getting your feedback on some of the modeling studies that we've just started. So I'm leading the evaluation of the short-term forecasts systems during MOSAiC. The presentation that I'm giving today is focused on wintertime statistics. So that's October 15th, 2019 to March 15th, 2020. And the motivation for this work, so this is a figure showing the skill of Arctic forecasts from a number of different state-of-the-art forecast systems. This is 0 to 60-day lead time. This is showing the skill of sea ice volume. The horizontal black line with the gray shading is showing the skill of a climatological forecast. And the black line is showing the skill of the persistence forecasts. And then all of the different colors are showing the skill of the different state-of-the-art forecast systems. And the first thing to note is that at a 0-day lead time, persistence forecast is beating all of the different forecast systems. And that's because of the limited data available to initialize the models. But what's really interesting is that after about 2 weeks, all of the models have less skill than climatological forecasts, except for this one yellow line, which is showing the skill of the most current ECMWF forecast system. And what this is indicating is if we can understand the biases in the physical processes and improve their representation, we can improve the skill of these forecasts beyond 2 weeks. And that's the motivation of this work, is to understand the biases and to improve our representation in these Arctic forecast systems. So this is showing the observed bimodal distribution of the net surface long wave fluxes, so outgoing minus incoming. And that's what's shown here on the y-axis. And on the x-axis is showing the low level stability. And so on the left, this is from the arm site at Barrow, Alaska, and on the right, this is from the Shupe campaign. And that was a campaign similar to MOSAiC, that a year-long drift experiment that took place about 20 years ago. And so what you can see, both of these show a bimodal distribution. So there's a clear sky mode where there is very large outgoing long wave radiation, about peak of about minus 50 watts per meter squared, and large low level stability. So the surface is cooling much faster than the atmosphere, is causing large inversions to form. And the second mode is a cloudy mode, which has much smaller surface net long wave radiation. The incoming and outgoing radiation tend to balance, and much smaller low level stability, because the cloud-driven mixing is reducing the stratification. So this is showing the same diagnostic, but for 11 CMIP5 models. And so this white line went right through the clear sky mode in the previous figure. And so what you can see is that most of these models have only one mode. So that's because they're missing a cloudy mode. And that's because most of these models tend to have a real difficult time simulating liquid and clouds at very cold temperatures. But what is also very interesting is if you look at this one mode that you see in all these different models, they tend to occur. So this is the clear sky mode. They can occur for very different net long wave radiation. This one's about minus 30, whereas this one's minus 60. And also the low level stability tends to be much smaller than what was observed. And that's another very common bias in these models, is that they're really challenged in simulating very stable conditions. So the project I'll be talking about is called the MOSAiC Near Real-Time Verification Project. It uses observations taken during MOSAiC to improve simulations of these processes that are unique to the Arctic, such as the persistence and the maintenance of mixed phase clouds. Those are clouds that have both liquid and ice. Also, the representation of the stable boundary layer, the interactions between the atmosphere and the snow and sea ice, and also the coupling between the ocean, the sea ice, and the atmosphere. And we're focusing on these short-term forecasts because in order to identify the errors in the fast processes, such as cloud feedbacks and surface fluxes. So the observations I'm using in this analysis are observations of the sea ice and snow taken from the L site. So those are the 3 sites about 10 kilometers away from the polar stern, where this is called the seasonal ice mass buoy, measuring, it has a thermistor string that goes from the atmosphere down into the ocean. And from the 30-meter tower, which is shown in this figure here in the middle, and the 3-meter flux stations at the L sites. And then the GOE arm measurements, which primarily were located on the polar stern. There were some on the ice, but I'll be using observations that were taken from their radars and LIDARs that were on the ship on the polar stern. So the model that I'll be talking about first is called the NOAA Coupled Arctic Forecast System, or CAFS. It's the coupled Arctic system that we developed here at NOAA and the University of Colorado. We ran this model. We did 10-day forecasts every day during the MOSAiC campaign and provide forecasts to the ship in support of the scientists. And so this model uses the WRF atmospheric model, the Los Alamos SICE model, the POP ocean model, the NCAR land surface model, and all of these models are run at 10-kilometer resolution. We use AMSUR2 to initialize the sea ice, NOAA SSTs to initialize the SSTs. We initialize the atmospheric state with the GFS, and we initialize the cloud fields with the previous day's forecast. So the way that I set up this study is I first tried to put together the diagnostics to understand the processes and the biases in the processes using the CAFS model, and then I included the other models that I have. So I have about 7 different models right now that I'm using in my evaluation. So the first figures I'll show are just the evaluation of the CAFS model. So this is showing the relative frequency, or the PDF, of the net long-wave fluxes from the flux stations in black. The red is showing the results from the 1 to 2 day CAFS forecast, and the blue is showing the 5 to 6 day forecast. And if you look at the black first, you see this bimodal distribution. You can see that the model, this CAFS model, is doing a very nice job of simulating this distribution, except that the CAFS model is 2 bimodal, so it's either clear or cloudy with very few thin clouds, which is very interesting and something I'm looking into. But I'm calling clear sky as net long-wave fluxes less than minus 35 watts per meter squared, and cloudy sky as greater than minus 15 watts per meter squared. So this is showing the sensible heat fluxes at 10 meters. So this is from the tower. The flux stations were only up to 3 meters. So this is the 10 meter from the tower. On the left is the cloudy sky. So long wave net greater than minus 15 watts per meter squared. And on the right is the clear sky. So long wave net less than minus 35 watts per meter squared. The black are the observations, and the red is showing the model. And if you could look on the left first, this is very interesting. It shows that when you have a cloudy sky, the sensible heat fluxes are primarily positive, so out of the surface. And I thought that was so interesting. I did not expect to find so many unstable cases in the middle of winter. And you can see the model's doing a really nice job of simulating this distribution. On the right, this is the clear sky, and you can see that the sensible heat fluxes tend to be negative, so downward fluxes. And you can see the model is shifted to the left. So the model distribution is the fluxes are too large for clear sky relative to the observations. And this is just the cumulative frequency to show on the left, the cloudy, that this green bar is just showing the 0 line. That's showing that 80% of the time in both the model and the observations, the fluxes are positive for the cloudy skies. And on the right, you can see that for 95% of the time, for clear sky, we're getting negative fluxes, so downward. And this shorter green dashed line is showing just this bias that we're seeing in this CAFS model, that for minus 10, which is the peak in the PDF for the observations, we're getting about minus 10 is up to, so fluxes less than minus 10 occur about 35% of the time, where in the model it's more like 55% of the time. So this is a very interesting diagnostic. It's the scaled sensible heat fluxes, which is sensible heat flux divided by wind speed relative to the near surface stratification. And this is a really interesting diagnostic because it tells you something directly about your parameterization. So this slope of this line is telling you what the transfer coefficient is in the bulk parameterizations for your sensible heat fluxes. So the upper left is for the observations, so the black are the 10-minute average from the flux stations. And the red is showing 5-degree bins. And I'm doing the flux stations, each one independently. So you see the 3 dots in the vertical for each of the flux stations. And so you can see for negative stratification, so the cloudy skies, we're getting scaled sensible heat fluxes between 5 and 10, which decrease as the stratification goes to 0. And then you see as the stratification becomes positive and increases, the scaled sensible heat flux goes to 0. And that's very interesting because what that's saying is that when you get very stably stratified surface layer, boundary layers, the turbulence gets shut off. And that's something that was found for the Shupe campaign. And so on the upper right is the same diagnostic for the 1 to 2 day forecast. The lower left is the same for the 1 to 10 day forecasts, just to show that our statistics do not change for longer lead times. And the lower right are the binned values. So the red from the observations, I don't know why it keeps doing that, and the black for the model. And so you can see that the model's doing a very nice job of getting this distribution for the cloudy skies, for the negative stratification and the large scale sensible heat fluxes, and a pretty good job of getting the slope as it goes through 0. But then you can see for positive stratification, the fluxes are too large. Also, you can see we're not getting any of the very highly stable cases. And this is very interesting because this is the SICE, the Los Alamos Sea Ice model parameterization for the bulk sensible heat fluxes, which takes into account the similarity functions that were developed using the Shupe observations. So you can see that we're getting, this is something that was found for the models when they were evaluated with Shupe observations. So before they included the Shupe observations, we're getting the same result, that the sensible heat fluxes are too large, and the model cannot create these very stable boundary layers. So it's going to be very interesting to understand why this is happening. So here I've added 4 other models to this. This is that diagnostic I showed at the beginning. The long wave net on the y-axis and the near surface stratification on the x-axis. And here I've added the ECMWF model, the IFS, the German Weather Service, the DWD, the Météo France short-term forecast system, the ARPEGE, and the Russian Hydromet forecast system, the Slob model. And what you can see is that the CAPS model does get this bimodal distribution. It's 2 bimodal, as I said before, compared to the observations. But none of the other models are able to get this bimodal distribution. The Slob model seems to only get this cloudy state, but that's something I'm looking into because the liquid water path is too small to really call that a cloudy mode. But if you look at the lower 3 models, you see that they only have a clear sky mode, but that the stratification is still much, much smaller than what was observed. And this is that scaled sensible heat fluxes again, compared to the near surface stratification. Again, the Slob model has a very different distribution from all of the others. It does seem to have more stably stratified cases, and this decrease, there's these black dots, how they decrease as the model becomes more and more stable, which is very interesting. I now have all the documentation for all these models, so I'll be looking into how each of the models represents these different processes. But if you look at the lower 3, you can see that not only do they have sensible heat fluxes that are too large relative to the observations, but they also, just like the CAFs, do not have stably stratified cases, highly stable, beyond 3 degrees. But in addition, they do not have the cloudy sky distribution either. You can see that the sensible heat fluxes barely go above 0. So in summary, I've shown that these short-term forecasts of the Arctic Ocean sea ice atmosphere coupled system are very useful for identifying biases in fast processes, such as the surface fluxes and cloud formation, but that these state-of-the-art models are still struggling to maintain liquid water at very cold temperatures. And also that maintaining the near-surface stable stratification in winter, it's critical to simulating the surface fluxes and the coupling between the different components of the climate system. But this analysis has shown that that the stable stratification, even in these current models, cannot be maintained, partly because the sensible heat fluxes are too large. But this is even though we're taking into account the relationships that were developed for the very stable conditions that were observed during Shiba. And I wasn't able to show this in this talk, but this weaker stratification is causing the snow and the sea ice to be unrealistically sensitive to atmospheric variability, which is really biasing the evolution of the sea ice. So thank you very much. I look forward to hearing your questions.